I'd like to introduce Dr. Karl Andersson, Research Officer, Soil Carbon Officer for New South Wales DPIRD. A soil scientist with 25 years experience throughout New South Wales, Karl has worked in regions from the high rainfall to the semi-arid zones in fields including soil mapping, agronomy, soil carbon, nutrient cycling, irrigation and dryland and urban development. Karl is based at Tamworth Agricultural Institute and works to enhance soil management practices within the New South Wales agriculture sector and is an experienced researcher and communicator of soil carbon information.
The purpose of today's talk is really aimed at producers and their advisors considering what you can do to manage soil carbon, not specifically how to increase it in one or all areas, but to be informed about the processes in soil and what you can expect of the dynamics to result in a change, and considering any sort of involvement in carbon trading schemes. The outline is to look at soils in the landscape, interpret what you've got in front of you and under you, consider the processes that influence soil carbon, then looking at some data that you might be able to access or do have that you could use to ballpark your soils, and then consider steps for a soil carbon project. Firstly, what is it? What are we talking about? Soil organic matter is basically the stuff that's come in through plants, processed through animals and microbes. It's brown or black. It's dark in the soil. We can see it. It provides lots of great attributes to the soil, turns it from dirt into soil, and it's basically what you want. Carbon, the soil organic carbon, is the carbon part of that matter. We measure that in the lab, usually given as a percent of the soil mass, and it gets respired. As it gets respired, nutrients are cycled out of the organic matter. Bulk density is a term that says how much soil there actually is in a given depth, say per hectare, and combining carbon percent and how much soil there is gives us a carbon stock, how much carbon you have in that hectare per depth. And if you're in trading schemes, that's what they want. The equivalent soil mass is if you're thinking of sampling between one time and the next, you want to get the same amount of soil so that you're not inflating or undercutting the amount that you have been estimating. And then carbon fractions or pools is something you might hear, which is basically talking about the decomposition of the organic material. Terms like particulate, labile, humus, mineral associated, pyrogenic or charcoal, those sorts of things just represent where organic matter and carbon is moving through. So some context about what we're talking about. I'm going to have a series of profiles from different places and see what they show. So what we've got here is two soils from different parent materials in high rainfall area. Basalt on the left and a granite on the right. The basalt's from Batlow and granite up past Tumbarumba. We can see that there's a concentration of dark material in the surface. That's our organic matter. It fades away as we go down, and in the basalt on the left there, it's gradually depleting as we're getting more clay and redness, which is the iron in that soil, coming through. Quite a different soil developed on the granite. There's more sand in it. Over time, the sand sort of shake to the top and the clay shake to the bottom, and we get this difference of sort of sand over clay. And that helps that organic layer stick out so much more, very distinct. In this sort of soil, the water comes in, hits the clay, parks a bit and starts dissolving things and ends up leaching them away. So we end up with this pale layer. Now, organic material is dark. Where it's not dark, it's over to iron for our colour. And if iron's gone, then pretty much everything's gone. And this is a fairly infertile material. So long as we've got this on top, the job's right. How quickly can those changes happen in the landscape? Very quickly. And we can step over some of these changes sometimes. You can see that in this paddock here. You might see granites as basalt caps sometimes in your landscapes. Take that same granite material and move it from Tumbarumba up in the highlands, coming through Wagga and then out towards sort of Mount Hope, pushing into the western rangelands. Same granite material, very different profile development with rainfall. The Wagga one has still got a dark material on top and a bit of a pale layer there, and a shallower soil as well for the same sort of place in the landscape. The one out west, much lower rainfall, doesn't have that pale layer at all and doesn't really have the organic stuff at the top either. So different soils giving different properties. Thinking about how you relate this back to when you have some numbers, what you're sort of seeing, what they can tell you. An example of running down a hill, shallow soils at the top up here, not much to grow with. As we go down, we get deeper soils. We've got something more to work with for roots to get into, water and nutrients storage and access. Getting down the bottom, we might have an accumulation of organic matter at the top with more moisture being supplied in those areas. Again, changes of soil type just down the slope. Think about how your numbers might relate to this. These sorts of changes don't just occur on hill slopes, of course, they occur on alluvial areas as well. We can have these stream channels depositing material as they flood and overflow their banks. The sands are heavy and they get dropped out first. As you move away from the channel, the finer sands and silts and some clays get dropped out in these red soils here on the meander plain area, and then further out back where the really fine material gets carried and then left behind as the water evaporates. We get these heavy clays. Again, we can see in this picture on the right-hand side here how those changes happen away from the channel. And we've got little island relics of previous building of this landscape. So lots of changes can happen. So that's sort of some context about how to interpret numbers and how you can look at your data. So moving into the processes that influence soil carbon. I've referred earlier to some of the pools in the soil, and what they sort of give us is indications of processing. The particulate material is labile or relatively easily accessed and decomposed. As we get into the soil, we've got a structured soil, say, that provides some sort of physical protection where roots and organic matter can sort of hide away. As the organic material gets processed, it ends up with sort of active charges on the side of it, which can mean that it can then stick to other charged surfaces in the soil, like clays or oxides, which provides a measure of chemical protection from degradation. The source of it all, of course, is photosynthesis, carbon dioxide being brought in through the plant, which ends up as litter or cycled through manures, the root biomass in the soil, and the all-important exudates get cycled through organisms into soil organic matter, but a lot of it, of course, gets cycled back out as respiration. The more disturbance that we have in a system, the more air gets into the soil for the organisms to respire with, so that increases the respiration of carbon. We have product removal, of course, and hopefully not too much erosion, losses off the soil. We can see erosion though. The key point about this is, if you're thinking of building, well, first you've got to maintain. We can see the little undulations, the convex and concave sort of slopes in this paddock where, thinking back earlier to the colours running down a profile, we've got the darker surface soil, the topsoil being sort of washed down into these sort of hollows here and being stripped off the steeper bits. It gets sort of moved out of the system in the end sometimes. Similar idea out west in the rangelands, where Tongway and Hindley's idea was about, is a system accumulating resources or losing resources? And out in the drier areas, of course, rainfall becomes so much more important, and capturing it in the system rather than losing it and the resources with it is really important. Some cropping examples where we've got the surface protection of stubbles from wind erosion. John Lees took this neat photo showing how dust is kicking up at the edge of the stubble effect. And then the top one here with bare soils being exposed to summer storms really rips it away. And of course, sometimes erosion is all too easy to see. So what happens below ground? What sort of processes are going on down there? Well, root growth is concentrated mainly at the surface, and deeper roots tend to grow through pores mainly of previous roots or channels being built by soil organisms. Just because soil is heavy, getting down there, it's hard to push around, so you find a lot of it in channels. Rainfall has an effect not just at the surface with that plant growth, but what happens in the soil. And so we've got a difference of sort of drought accumulation and mineralisation happening. The microbes respond quickly to moisture and are active at lower water concentrations in soil than our plants. And with Australia having the most variable rainfall in the world, it really means that we've got this stop-start system a lot, where a plant can sort of grow a bit and accumulate, but then bugs can attack it. But this idea of sort of droughts and mineralisation is where you might think that in a drought there's not much input, but if the bugs are parked as well, we can have an accumulation of organic matter towards the end of a drought, and then the drought breaks, then the bugs kick into gear and drop it down, mineralise it out. That's one of the reasons in agronomic sense we don't test straight after a drought, because we get overinflated P and S type measurements which are coming out of the organic matter. So what helps us retain organic matter longer in soils? I referred earlier to the mineral and the physical protection. We've also got the importance of nutrients and the cycling. So carbon levels are related to nitrogen, phosphorus and sulphur in soil being part of organic matter. And we find fairly consistent ratios in the stable sort of pools. And having a good supply of nutrients in the soil actually helps hold on to carbon for longer. Depth is also an important factor. And generally we find that the carbon at depth in the soil is much older. So the idea becomes, well, if we can get more material down there, then that will stay there for longer. What influences shorter residence time in soils? The idea of priming, which is like activating processes. Fresh organic matter and nutrients can be a source of substrate for organisms, so that can kick into gear and start decomposing. We can look at ameliorating constraints to plant growth, which means more input, but it can also allow bugs to get active again. So it's been found where sometimes where lime's put on, that's overcome a constraint for the bugs and end up with lower organic matter sometimes. Exudates, all important, so much going on with exudates into the soil. Some of those actually can liberate what we thought might have been protected, the mineral associated organic matter there, where the material was stuck onto the soil, but that can actually now be released and mineralized by plants. And there's some really cool stuff we've relatively recently found with iron, where some of the reactions can inorganically, so independent of microbes, start to break down organic matter, which sort of puts a bit of a limit on how far we can get with the material. The flip side of the depth story is that material that's there that's older, like you could measure something where the carbon at depth is like 4,000 years old. But what that can mean is actually that it's taken 4,000 years to get there, and all we've got is, say, 0.5%, so not much actually gets there. Not only can the fresh organic matter that gets put down there be decomposed, but the flush of nutrients or energy that it provides has been seen to sometimes actually get the bugs going, and they decompose not only that fresh stuff, but the soil material that was already there. All these interesting cycles that are going on. What does carbon look like at depth in the soil? Here's some charcoal in this top left, and now we've got one here where you can see the old surface down the bottom, where the top 20 odd centimetres of material has been deposited from upslope. But what we're really talking about at carbon at depth in the soil, from this sort of management point of view maybe, is looking at these sorts of patterns here, where we've got a root material. You can see that it's decomposed into this darker material there, and it still sort of provides a channel for more recent roots to come through. Here's quite an extensive accumulation of material in this soil here. These photos I've got for carbon at depth, they're in the sort of minority, and what you can see is that with this accumulation, it stands out because there's not much around it. So there's generally a lower level of carbon in that depth in the soil compared to the surface. There's some of those context and processes. Now, so we're at the position of having some data available, and how do we ballpark ourselves amongst that? These two profiles here that we saw earlier, the carbon levels in those in the 0 to 10 centimetres, we can see there 3% in the higher rainfall area with the darker soil and only 1% down at Wagga. Into the 10 to 20 centimetres, both soils, they're dropping down in how much organic matter is in their soil. It's a typical sort of pattern that we find with the decreasing carbon with depth. Here's a study from the Hunter Valley, 2,800 hectares with various parent materials and quite a range in elevation of 120 metres from hill slopes and ridges to valley floors. Concentration of carbon at the surface and decreasing with depth. All those black dots are the many holes that they dug, but the median value is the red line here, fading away. Bulk density, mentioned before, that tends to increase with depth. Light and sort of fluffy at the surface and increasing sort of with massive soil. We're getting up to these sort of 1.5, 1.67 levels. Generally, your bulk density would be between, say, 0.8 to 1.5 would be a normal range. A bunch lower here. These ones pushing above 2 are very high, very high. Anyway, that's the sort of normal range. Bulk density doesn't tend to change as much in your soil as carbon, unless you're in there disturbing it or compacting it. Carbon would change more so than bulk density. Combining those two, we get the carbon stock in the soil. Again, reflecting the organic carbon percent, but sort of moderating that a little, sort of a bit more compacted. What that's ended up like in this study was this here, where we've got the range from low carbon stock to high carbon stock in the surface, 10 centimetres. And you can see the patterns here where you've got low levels on the ridge tops and higher in the valley floors, thinking about that stuff we were just showing earlier. Some of these lighter red areas are also places that were sandy, light parent material, so sands don't hold onto organic matter and carbon as much as clays. Some patterns of profiles from further out west. At Cobar here, we've got some concentration at the surface, tailing away with depth, but not as high, so 0.8, not as high a number as we have east. Going further west and south, much lower levels again, so 0.3 and dropping down. And these funny patterns here, increasing with depth, might be artefacts of some of the funny things that happen in soils out west with inorganic carbon. So an idea of the types of range of carbon percents that we see, carbon stocks that we see in soils. You might have your own numbers, or maybe part of a group who can share numbers to have a look at. And here's a group that we had up in the tablelands, or the tablelands, where we got 40 odd paddocks there assessed, and ranges from down below, so around 1%, 1.2% in this orange bar, moving up through, pushing towards 2% now, but getting to 3, up to 5s, and then a bit of a bell ringer here. I've included that one just to sort of point out that when you're taking samples, it's really important what you collect. This one happened to have a whole heap of litter and kangaroo poo in it, so you send it off to the lab, it's going to be high. So careful about what you sample and what you're looking at. These soils were taken from a range of soils from granite and sedimentary trapped materials and basalts, and they were basically reflecting granites, trap and basalts in those. Take those parent materials and move to Ebor on the escarpment where it's colder and wetter. And those numbers of 1, 3, 5% become 2, 5, and 8, 9, 10%. Effective climate really increasing the level of organic matter in the soil. Go down to Tamworth and our numbers are lower again. A bit hotter, a bit drier, and we can see less. So we've got, our 0 to 10 and 10 to 20 centimetre samples. And we can look at those and have a bit of a check. These ones here where there's more underneath than there is on top. Again, be careful about what you're sampling. Maybe there's some mislabeling of bags, and if they're legit, then they're interesting, worth checking out. So from this sort of stuff, could you say that, well, these ones here at 1.5%, they should be 2.5% or more? Well, you've got to think about the stuff we've talked about with what are they on and whereabouts are they in the landscape. Put yourself into context and see what those things sort of tell you. In a broader sense, down south in the Riverina here, and what we've got here is in the 0 to 10 centimetre increment. The colours are showing reds of low moving to green and brown and black, sort of showing what the soil colour looks like. Lots of variability within there, but some of the patterns we see is where there's irrigation out here, there's higher amounts, and some of these areas out here with irrigation. In lighter country, there's low numbers. Where there'd been a bushfire had gone through, there's lower numbers. But in general, what we're getting is south and east, as we're getting higher and wetter and cooler, the amount of carbon is increasing as we go there. In the 10 to 20 centimetres, most of that's not there. It holds with the profiles that we saw earlier. There are cases where there's higher numbers at depth, which is worth checking, and then interesting to look at. But generally, a lot of that is disappearing, mainly concentrated in the surface. So how does carbon behave in the soil? Historically, there's been a general pattern of losses, decreases of our organic matter and carbon with this sort of pattern. The 0 to 10 is in the top here. There's a rapid drop with time since cultivation, or years of cultivation, and it starts to flatten out. Similar in the subsurface, we've got a drop and then it flattens out as well. Just that idea of microbial processing, more aeration in there, they can process more. There's also part of this would have been erosion losses as well. Similar again, another study long-term looking at patterns there, mainly clay soils here, dropping away in a similar sort of way. And what went with that was decreasing productivity. So we can think about carbon for just accumulation, but it's also a key part of productivity. Keeping an eye on this is, we're obviously not wanting that to happen. So that's a thing to be managing. So we get losses and we get recovery. There's a lot of studies showing recovery in systems around the world and throughout Australia with these sorts of rates: half a tonne, 1 tonne, 1.2, 0.2, those sorts of numbers over periods of 5 to 8 and 20, 40 years. One little update to this one is that the study here around in the Central West near Cowra, in 6 of those 8 sites, they've dropped back down in the subsequent sampling just recently. So there's cycling that happens. The ones that retained were one with a really low grazing pressure, and the second one with a whole heap of pea being thrown at legumes to maintain its level. The key thing then becomes sustaining a recovery. We can get an increase with more inputs or less outputs, but having that stabilise and sustain is the important thing. So we increase our organic matter, but we've got to keep that organic matter coming because the bugs will keep going. So to increase, we need to keep that happening. These 2 plots here are showing data from really long-term trials in UK, Rothamsted, you may have heard of, We've got a bit of control running along the bottom here in our top graph, just sort of sitting there. We had applications of manures which were then ceased, and it started to drop back down. It increased, but then it started to drop back down, still higher. The condition of the soil was improved. Not all disappeared, but where organic matter has been continued to be applied, increasing further, but the majority of it still gets mineralised. It starts to approach a ceiling. Similar sort of story down in the bottom graph here, where we're starting on a cropped site. It sort of bumped along the bottom, increasing a pasture. The amount and the consistency of production and the decrease in disturbance saw an increase in carbon levels. Vice versa on the pasture, where it was maintained, it's poking along, but where disturbance and intermittent growth has been put in with cropping, it's dropped away down to that lower level. So the idea then is that processes or increases don't happen indefinitely, and in Australia they don't always just happen as easily either. There's limitations of rainfall and nutrients and the initial carbon stock as well. How close to the ceiling are we? Now, if we're not getting an increase, that's actually not a bad thing. It's actually a good thing, because it's showing that the system is working, the system is dynamic, and the soil is functioning. So, as long as you're not at a bad level, then cycling is good. The nutrients, I've mentioned carbon, nitrogen, phosphorus, sulfur earlier. Here's some work from Ginninderra over a 20-year period where applying P was able to increase, and not just in the surface, increase the carbon stock through depth down to 60 centimetres, at around half a tonne a hectare a year. I think it's got up to about 12 tonnes in the end. So the importance of fertility in our systems. Ginninderra is near Canberra. Here's some work from Condobolin in the central west of New South Wales, where over time different rotations were being implemented, and carbon was one of the things being assessed. We've got increasing carbon levels over this 13-year period, which is great in all the rotations. Continuous crop, cultivation, permanent pasture, reduced till, increasing there, and it was even starting to bump into the 10 to 30 centimetre layer. Same treatments there, of course, but it didn't sustain. Dropped down in both. Dropped down to sort of at or below where they were. From 2012 to 15, was that due to it rained and bugs got active? There was activity for them to start mineralising. Not quite fully explained, but we get this idea of that you're operating within an envelope. There's inputs and there's outputs, and as long as you're on a good path and a climbing plane, say, hopefully, then that's good, but it's not just a one-way story. Grazing management is often seen as a way to be increasing soil carbon levels. But Sarah McDonald led a review published last year, looking at 30 papers where grazing trials and carbon levels were managed or measured in Australia. And overall, they found that there was no significant impact from the different practices. Now, that's not to say that grazing management doesn't influence soil and productivity and the drivers of soil organic matter. More plant growth, herbage mass, ground cover, residual biomass, and productive perennials, all found as effects, but no change consistently to the soil organic matter. And again, that's not necessarily a bad thing. It's a sign of a functioning soil. Where could our opportunities be? So John Gray's got this work with others looking at the opportunities through New South Wales. The process was to look at a 10% increase in long-term vegetation, whether that was re-veg, grazing management or stubble management. And the results come out with sort of low increases expected out west, whereas dry, the sorts of reasons we've been talking about. Patchy influences you can see through the area. Low again where there might be high stocks already, but potential to increase in some of these areas like the Liverpool Range or the basalts out of Glen Innes and running down the McIntyre, those sorts of areas. So these sorts of things can be really useful in helping identify areas of greatest potential to increase soil carbon levels. With all that in mind, considering a soil carbon project, so the first step you'd be looking at is estimating the amount of carbon in your soil, ballparking the potential of where you might be able to get to, definitely managing constraints and thinking about what changes you could make, what's eligible, what would fit for you, and then what you'd do with any credits. Would you sell them to someone else to offset their emissions, in which case they're not yours anymore, or would you keep them to inset them against the demands coming from the market and the supply chain. In terms of addressing constraints, here we've got a really compacted soil, really hard, a lot of time for roots to get established in that and grow around. So making that a more amenable environment for plants is a thing to address. Acidity, we've got a patchy lucerne stand here. We can see these signs sometimes, and that's shown in this really trimming off of the roots. Organic carbon here in the yellow, a bit of accumulation in the surface and running down, but low levels there. And the limitation here was acidity with aluminium, really toxic at that layer. So addressing that would help better plant growth, better cycling and inputs. Having a surface soil like this is not real nice for plants to try to get into. So dealing with that type of condition is doable. You can assess it yourself, and getting onto that is definitely a thing to do. Another thing of soil stability is this idea of slaking. And you can assess this by putting some soil into water, and you can see that the darker one, it's organic, it's staying together. And the one that's lower in organic material is falling apart. And I mentioned before that like a good amount of organic matter is where it's staying together. Salinity is something that we could look at managing, especially out west, where there's natural levels of salinity. At this spot, we're basically looking at seawater. But if we could move that down the profile, then plants can get established, and we can start to get some more, not just productivity, but maybe some increase in carbon in our soil. Where does the system let you in? Here are the list of practices that are eligible under the ACCU scheme. And big table, basically they fall into these things we've been talking about by and large. Ameliorating your soil. Irrigation is one where you put more water on, more plant growth. Managing pastures, managing cropping, engineering the soil, whether that's land forming or delving, say, or getting legumes and cover cropping into the system. All eligible activities for a change to measure pre and post carbon stocks. Going down that way, there's commitments involved, and you'd be thinking to yourself and talking to others, like the documentation around this is hundreds of pages long, and there's lots of calculations. So you'd definitely be having advice and talking to service providers about what's involved. What commitment is required from you to practices, sort of time frame, where does the risk sit, and what options do you have if you decide that doesn't work for you in the end? Would they be helping you take some preliminary measurements to help understand where you're actually at? Do the statements maybe sound too good to be true? Are they offering guarantees? Are they suggesting an infinite capacity for putting carbon in your soil? Are they saying that just changing practice is easy? Do they dismiss any science, just saying it's BS? All of these things I've heard in public forums. How much extra biomass is actually required to get more carbon in the soil? How long would it persist? Is there new biology? That could be an answer. Basically, what evidence is there? Are there examples of success relevant to you? We've seen lots. I've shown different things that can work. Are there things around that can work for you? Are there examples, importantly, of things where changes weren't measured? And how rigorous is any proof? So the key points that just summarise is that what do you have to start with? Look at the variability in your paddocks and look for key properties and assess your starting point. What might you be able to get to? What do regional levels suggest? What sort of capacity is there for you to get to? Building organic matter and carbon is about getting more inputs, more growth, and less outputs, less mineralisation, loss. The evidence base, there's a strong evidence base of showing historic loss, and that recovery is possible. However, it's not always consistent. It's not always easy or sustained, and doesn't necessarily mean that we're going to get back to where we were. It is harder to build than it is to deplete. And while we have a good, firm general understanding of the processes, it's how they actually play out in the paddock that's the real important thing. And having some more work and long-term experiments to look at the dynamics and how long changes are sustained is an important thing that we're still doing. If you're looking at a project, you'll see how it fits you. And in any case, you want to be managing nutrition, your productivity and erosion with the real benefits that we know about from maintaining and cycling of carbon and organic matter. Some of the few studies that have been able to quantify this have sort of point to values of $100 a hectare for having better, higher levels of organic matter in your soil. So that's about it. So that's it from me for now.